Hey everybody, welcome back to Complex Analysis. So today we're going to be talking about topology of the complex plane. This is going to be a two-part episode because we have a lot of definitions to get through, and I want to take my time with them. In any case, before we get to the topology that we need for this course, I want to give you a brief overview of what topology does, or what we do in topology. Whoops, don't look. There we go. All right, so topology is the study of geometric properties and spatial relations unaffected by continuous change of shape or size of figures. So a classic topology joke is that a topologist cannot tell the difference between a coffee cup and a donut. And the reason for that is topologists are trying to see whether objects are equivalent to each other by taking one and morphing it into the other. So here, if you look at the GIF, what's happening here is we're taking a coffee cup and we are changing or morphing it into a donut. Okay, so here's the start. So what we do is we raise the inside of the cup, okay, and then we sort of just massage or we fold the rest of it into a donut. Now, when we do these foldings or these morphings, notice we're not changing the hole. Notice there's still a hole. We're not getting rid of the hole, and we're also not poking any extra holes. So topologists sort of take objects and they morph them into other objects in this way. So it's sort of like you can blow up certain parts, meaning you can stretch certain parts and you can shrink, but you can't tear and you can't poke holes or anything like that. So that's what topologists are typically doing. Now, what we're doing in this course is we're not sort of getting at the geometric properties. Well, kind of a little bit, but we're not getting too deep into it. Basically, we're going to be covering a little bit of what's called point set topology, which deals with open sets and closed sets. And that's what we're going to jump into very, very soon. All right, so let's get started with the topology that we need in our class. So circles in the complex plane are sort of our natural quote-unquote open sets that I was referring to yet. I haven't defined what an open set is, but we'll get to that in a second. So recall that if we have 2 points in the complex plane, so let's say here's Z and here's W, if we take the absolute value or the length of the difference between these 2 complex numbers, we just get the distance between them. So this distance right here, let's call this R. This is equal to the length of Z minus W. Okay? So if you ever want to find the distance between 2 points, just take the absolute value of their difference, or the length of their difference. Okay? So using this idea of length, or modulus as we call it in complex analysis, we can actually define circles and open disks using this idea here. Okay? So we define a circle, CAR, as the set of points Z whose distance away from A is R. Okay? And we denote that with C, capital C, bracket AR. So really what this is in English, this is a circle of radius R centered at A. Okay? And notice we have an equality here. We're saying it's the set of points whose distance away from A is exactly R. Okay, so just to show you a picture, why this is giving us a circle, let's say this is the point A. So if we're trying to find all the points that are distance R away from A, well, let's go out R units in every possible direction. Okay, and notice what shape is this giving us? And by the way, we can't do this for every point because there's infinitely many points. But if we go out our distance away from A, notice that we do get a nice little circle. Okay? So that's how we define a circle. We define circles in terms of our modulus or our length quote-unquote function. It's not a function per se, but in any case, that's what we're doing. Similarly, we can define the open disk in the complex plane as follows. So we denote it with D. So DAR, this is the disk centered at A of radius R. Now this is an open disk because notice here we have a strictly less than R here, so it's not actually including the boundary. So let's say A is over here this time. So now we go out our distance, okay, but now we don't include the boundary, but we want every point that has distance less than R from A. So we're including all of this now. So this right here, this would be D, bracket AR in this case. And over here on this side, this would be CAR. Okay, so this is how we define circles and open disks in the complex plane. We use the modulus. Actually, I'm going to shade this a little bit more. Now, it is important there, I want to point out again, notice that it's a strictly less than r, so that's why we're getting all of this inside here and why we're not getting the boundary, because we're not allowing for equality there. Did not mean to do that. Okay. All right. So I wanted to prove really quick. Notice that DAR intersects CAR is empty, meaning that the open disk does not intersect the circle. Okay. Which hopefully is intuitively true, because let's say if we had, and I'm going to use different colors for this. So DAR, remember, would be the inside. So let's say that's A right there. And then CAR would be the boundary. Okay, and then the red there is DAR. So just by drawing the picture, hopefully it makes sense that, yeah, these two do not intersect, because the green, that's the circle, and then the red, that would be our open disk there. Okay, but let's actually see a proof for that. So we're going to prove this by contradiction. So proof. We prove by contradiction. Okay. And what we do for contradiction, let's assume that there is some x that lives inside the intersection here. Okay. Assume that there exists an x inside our intersection here. Okay. Well, if this is true, then this means, okay, that, well, since x is in the disk of radius r, we have that x minus a must be less than r. Okay. But since it's also in the circle of radius r, this means that the distance between x and a is equal to r. But this can't happen, right? You can't have distance less than r and at the same time have distance equal to r. A contradiction. Okay. Therefore, the intersection must be empty. Okay. Now this is important because what we're saying here really is we're saying that the open disk is truly open. It doesn't have its boundary. Okay. And we'll see that come into play in a little bit. All right, everyone. So here's a collection of topological definitions that we're going to need in our course. Now, these come from, if you guys go on to either a topology course or in grad school, you'll probably first see this in what's called a point set topology class, like I was referring to earlier, point set topology, which again sort of deals with open sets and closed sets on sets. But in any case, let's go ahead and talk about these definitions. So let's suppose G is a subset of C. Okay, so I'm going to pick a subset here. So let's say G, let me use a different color. So there's our complex plane. And let's say G is this blob that contains this, and then let's say it's missing a little bit of this. I don't know, something like that, almost like a dog bone, right? So notice I'm going to shade it in, but I'm going to unshade it in a second. I am including everything in here. I'm just not including all these dots here. And let's say G also, let's say it also contains some random point on the outside there. So G is probably not the nicest set in the world, but I think this will be a good example for what we're about to get into. So let me erase some stuff really quick, because I don't want that to mess with the pictures. Okay, there we go. All right, so definitions. So we say that a point A is an interior point of G if some open disk with center A is a subset of G. Okay, Okay, so again, A is an interior point of G if some open disk with center A is a subset of G. So it's kind of like what it says in the name. It's an interior point, meaning it's in the interior. So if we look at our dog bone here, this would be an interior point of G, because if I draw the open disk around, this open disk around A, notice that it's completely contained within our dog bone, within G. So that's what we would say an interior point is. Now if you look at this point over here, on the outside, notice that any open disk I take around this point, okay, will not be a subset of G, because it'll contain, let's say, this point, or this point, or this point, or this point, which is not actually in G. Okay, so this would not be an interior point in this case. Okay, so an interior point is a point in G such that there exists some open disk that's centered at A that's also a subset of G. So basically we can fit an open disk around A, but we still live inside G. Do some erasing. All right, our next definition. My dog bone. No. It was a really good dog bone. All right, 1 second. I think it was like this, and then like this, and like this. But it doesn't contain that right corner. Maybe a dog ate it. Anyway, okay. So we say that a point B is a boundary point, okay, if every open disk centered at B contains a point in G and also not in G. Okay, so boundary points, again, kind of like what the name suggests. A boundary point is something that's sort of on the border. Okay, so let's say that's B. So this would be a boundary point. And it's a boundary point because if we take any open disk, okay, centered at B, notice we're going to get a point that's inside G, but there's also a point that's outside G. Okay, so we would say that this is a boundary point. An accumulation point C is a point if every open disk centered at C contains a point different from C. Okay, so for instance, let's go back to, forget where A was. Let's say A is down here now. So if we take that point A, this will actually be an accumulation point, because no matter what open disk we take, we can take this one, we can take this one, we can even get a little bit smaller. Okay, but no matter what open disk we take, notice that there's always a point that lives inside G that's not equal to A, but it's still within that open disk. Okay, so we would call C, whoops, actually we're calling it C, not A. Let me erase that really quick. Let's call it C. Okay, so C would be an accumulation point in this case. Again, an accumulation point is a point that if you take any open disk around C, you're going to contain C and some other point of G. Okay. Now, if we look at our sort of our lonely point over here, this would not be an accumulation point, because if we take any open circle, well, if we take this open circle, or open disk, I should say, it only contains our sort of our lonely point here, but it doesn't contain any other point in G. So this would not be an accumulation. And then finally D, we say D is an isolated point of G if some open disk centered at D contains no other point of G other than D. So our lonely point here, lonely is actually a good descriptor of this. This point here would actually be an isolated point. Because if I draw, let me redraw it again. If I draw this open disk, don't look, don't look. If I draw this open disk, okay, let's pretend like that's a good circle. If I draw this open disk around D here, okay, notice it contains only D, but it doesn't contain any other point at G. So we would call this an isolated point. Isolated. Okay. Now, hopefully these definitions or these terms are somewhat intuitive, right? An interior point, yeah, it's in the interior. Boundary point, it's on the boundary. And that's kind of like why we name them this way. There is some intuition behind these things, but it's good to have a picture that sort of locks it in place for you as well. So let's consider another set or subset of C. So let's let G be the point minus 1i union, so this means and, the open disk centered at 0 with radius 1, and then the circle centered at 3i with radius 1. Okay, so let's draw this. I'm going to try to be precise here, but we'll see. All right, so D 0, 1, so this is the open disk centered at 0 of radius 1. So let's say this is 1, let's say this is I, let's say this is negative 1, let's say this is minus I. So this first subset here will be all of this in here. So in here, I mean all of this right here. Okay. The point negative 1i, that'll be just this point here. Okay, and then finally 3i, so the circle, now it's only the circle of radius 1 centered at 3i, that'll be, let's see, here's 2i, here's 3i, so we'll just have a circle. Okay, but it's not including the interior there. Okay, so that would be G in this case. Okay, so G is this point with this circle and also this open disk here centered at 0. Let me erase some stuff. Okay. So first, what I want you guys to think about, where's the isolated point? Where's the quote-unquote lonely point? Hopefully you guys spot it. This would be an isolated point. Okay. If you take any point inside our open disk here, you're going to get what's called an interior point. And, whoops, it's also an accumulation point. Okay. Now, if you pick any point along our circle here, you actually get a boundary point. Okay, because any open disk we take around any point on the circle here is going to contain some point that's not in G as well. So notice here we have a point here, we have a point here, a bunch of points there that don't actually live in G as well. So here's just another example using our definitions. Okay, open sets and closed sets. So kind of like what I was hinting at earlier with point set topology. So let G be, again, some subset of C. We say that G is open if all its points are interior points. G is said to be closed if it contains all of its boundary points. Okay. So again, let me say that again. So we say a subset G is open if all of its points are interior points. Okay. G is said to be closed if it contains all its boundary points. Okay. So let me give you some examples. So an open set would be something like this. Okay, and everything on the inside here. So it's not containing its boundary, but it's just containing everything on the inside of this weird shape here. Because if I pick any point, okay, I can always fit a circle or an open disk inside our set. Okay, so this would be an example of an open set. Something that would be closed would be, let's say we're taking, I don't know, this like diamond shape. Okay. So this would be a closed set because notice it does contain all of its boundary points here. Okay, everything around the border here. Now it's not open because if you take any border point here, okay, you can't actually fit an open disk that's contained within our diamond here. So this is closed but not open. Similarly with the open set here, this is not closed because it doesn't contain any of its boundary points. Its boundary points are basically the dotted line there, which it doesn't contain. Okay. So with these definitions in mind, we define the closed disk. Okay, okay, as the set of all points, well, the closed disk, I should say, centered at A, with radius r, okay, as the set of all z and c, so all complex numbers whose distance from A is less than or equal to r. Okay, and we denote it with d bar, so remember that's kind of similar to our conjugate, but d bar AR, that would be our closed disk of radius r centered at A. So for example, let's say that's A, okay, and let's say that's all the points distance r away from A, then the closed disk would be everything in this case, including the boundary. Okay, and notice this is a closed set. I know we're saying it's a closed disk. It also is closed in this definition sense as well. Oops. Okay. Boundary of a set. So again, hopefully this is sort of intuitive at this point what these things actually mean, but let's give them a mathematically precise definition. So we define the boundary of a set to be the set of all, well, boundary points of G. Okay. So it's almost the same notation that we have back in Calc 3 with partial derivatives, but weird delta G we're defining to be the set of all boundary points of G. Okay. So that's why we call it the boundary, because it's the set of all boundary points. We define the closure of a set, okay, which again we're using that conjugate notation there. The closure of a set G is just the set G, and then you throw in all of its boundary points. Okay. The interior of G is just the set of all interior points of G. Okay. Again, hopefully these are sort of intuitive at this point and sort of self-explanatory. But let me give you an example. Let's say we're picking on, let's say, the complex number 1 plus I. And let's consider d 1 plus I, comma 1. So the circle of radius 1 centered at 1 plus I. So we'll get this shape here, and everything on the inside here, which I don't want to shade in because I don't want to mess with the picture too much. But so d 1 plus I, comma 1, that's going to be, well, here, it's all of this, but now I'm going to erase it because I want to point out some things. Okay, so what's the boundary of this open disk? The boundary, and I'm going to use a different color here, the boundary would be, well, the dotted line there. This would be the boundary of d 1 plus I, comma 1. Okay. Now the closure of our open disk is actually just the closed disk that we defined earlier. Oops. Okay. And what's the interior of the set? The interior would be, well, all the green that I just erased, but let me put it back. Interior of d 1 plus I, comma 1. Again, hopefully these terms are sort of self-explanatory, but I want to give you a picture of what they actually mean, though. Okay, and that's it for today. So next video, we'll be getting into more topology and collecting more definitions that we're going to need for the rest of the course.